These are some real numbers. And these are some complex numbers written in the form of a plus bi, in which I is equal to the square root of -1. Also, you have seen one-dimensional, two-dimensional, and three-dimensional vectors in which the numbers are usually real numbers. Linear algebra generalizes the concept of vectors into more than 3 dimensions, and instead of just using real numbers, complex numbers can also be used. A vector space consists of a set of vectors and scalars, which is closed under vector addition and scalar multiplication, meaning that the result of them is another vector. Vector addition is commutative and associative. There exists a null vector, and for every vector we have an inverse vector. The scalar multiplication is distributive and associative. And for 0, 1, and -1 we have these vectors. In three-dimensional space, we can write a vector as a linear combination of basis vectors I, j, and k, and the components a1, a2, and a3. Similarly, for any vector, we have a set of basis vectors, and every vector alpha can be written as a linear combination of these basis vectors. These basic vectors are linearly independent, meaning that we can't write them as a linear combination of other vectors. It's very useful to write vectors in the component form, but we should consider that, in this case, we limit ourselves to just a particular basis. In 3 dimensions, we have 2 kinds of vector products: the dot product and the cross product. The cross product can't be generalized to n-dimensional vector spaces in any natural way, but the inner product of 2 vectors is a complex number with these properties. For example, for 2 vectors alpha and beta, we have these expressions. The square root of the inner product of a vector with itself is called the norm of the vector, which is a non-negative real number and generalizes the concept of length. If the norm is 1, we are talking about a unit vector which is normalized. If the inner product of 2 vectors is 0, they are called orthogonal, which is the generalization of being perpendicular. A collection of vectors which are normalized and orthogonal is called an orthonormal set. Suppose that we have 2 vectors, alpha and beta. We can find the projection of beta on alpha and subtract it to find a vector which is orthogonal to alpha. If we divide these 2 orthogonal vectors by their norms, we have an orthonormal set. Now, if we have another vector, we can subtract the projections of alpha and beta and find a vector which is orthogonal to alpha and beta. By using this method, which is called Gram Schmidt procedure, we can change a set of non-orthonormal vectors to an orthonormal set. As an example, suppose that we have these 3 vectors. For the first one, we just need to normalize the vector and find e1 prime. For the second vector, we need to find a projection of e1 prime on e2 and then normalize it to have the second orthonormal basis. And finally, for the third one, we need to subtract the projection of the previous ones and normalize it to find the third orthonormal basis. Now we have 3 bases which are mutually orthogonal and also their norms are equal to 1. There is also a very important inequality called the Schwarz inequality, which is written like this. If you like, you can define an angle theta, which is not a real angle, by this expression. As another example, suppose that we have alpha and beta as 2 3-dimensional vectors and we want to find the angle theta. First, we need to find the inner product of the 2 vectors, which yields a complex number, and multiply it by its conjugate. Then we find the inner product of each vector with itself and put all these numbers in the cosine formula to find the angle, which is 45 degrees.